Hi, everybody, and welcome to Gravity Day. Okay, so for today, we want to talk about gravity and some of the effects that it has upon us. So, there are two big things going on here when it comes to gravity that matter, right? There's the mass, right? How much stuff is inside of something, and how close together the two objects are. And that's going to affect how much gravity there is between objects. So, it doesn't matter where you are. You could be here on Earth, you could be kind of like these pictures out in space somewhere. Gravity affects all of us. And those two big things, how much mass and how far away from each other the two objects are, well, that's going to be what affects it. It pulls on everything too equally, right? Is one thing that we want to get into, right? If you have two pieces of paper, kind of like in the picture here, one's all kind of crumpled up and the other one's flat, and you drop them, right? Well, obviously the flat one kind of like goes down much slower. The heavy paper one drops really quick. And the difference between them is air resistance, right? Air gets in the way of the big piece and not the little one. So, but gravity is still pulling on all the same atoms that are inside each of them equally, right? So the famous example for this is like a hammer and a feather, right? Oh, no, I'm getting ahead of myself here. If you have a hammer and a feather and you drop them, gravity is pulling on both of them equally. But the difference is the feather, it's got a lot of surface area to it, and that kind of gets in the way. So if you drop the two of them here on Earth, it appears like, the feather's being pulled much lighter than the hammer is. But in reality, they get pulled the same speed, right? And I'll show you that in just a little bit. The other thing, remember, when they're pulling towards each other is how much mass they have. Now, the hammer actually would have way more mass than, the feather would. So if you put them out there in space, let's say, if you put them out in space all alone without moving and everything like that, and you let them alone, basically the hammer is going to pull the feather towards itself because it's got more mass to it. But because of universal gravitation, they will want to come together. They will be, pulled towards each other because of that, right? And same thing, if you put anything out in space, if you had two pencils and you put them close together out in space and just left them there alone, gravity would pull them together eventually all on their own, right? Here's a great example of me, let's see here, dropping some things to show you the difference between, heavy things versus light things, right? So I've got a light little wiffle ball on this side, a golf ball on the other side, and when I drop them, well, they drop at exactly the same speed. Gravity's pulling on them equally. Right now, even though the wiffle ball is really, really light and the golf ball was heavy, here's another example, right? Pool ball versus tennis ball, right? I mean, the pool ball is way heavier than the tennis ball, but they're roughly the same size. So because air resistance really doesn't matter too much, it would matter over the long haul with these because one's smooth and one's fuzzy. But look, gravity pulls on them equally, right? When you see them in slow motion, gravity's pulling both of them, even though one's really light, the tennis ball, and the pool ball is really heavy. Gravity pulls on them equally, right? How about this one? This is the most dramatic difference I could find. Steel ball bearings, super, super heavy on this side. Ping pong ball, as light as I could think on the other side, right? They're both similarly sized and everything, but look, gravity pulls on them equally. They're both being pulled down. It's not like the heavy one drops really, really fast and, the ping pong ball drops really, really slow from it. There's a slight lag, and I think that's because the ping pong ball is a little bit bigger, so there's a little bit more air resistance. But you can see gravity's pulling on them equally, right, from it. And then, here's the famous example on the moon, right here on the moon. You've got the astronaut right here, when they were on the moon. He had a hammer on one side, a feather on the other side. And unlike here on Earth, where the feather would kind of like fly down, going back and forth because of the air, on the moon, there was no air at all. So when he drops, here you can kind of see the hammer on this side, the feather on that side. When he drops them, they drop exactly the same speed, right? There's no difference between the two of them when they drop.
For our Falcon, drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
There you go. So it's just kind of a cool thing. Let me see if I could rewind it. Here you go. When he I just didn't rewind enough. So when he drops them, here's the hammer, here's the feather, and they drop at exactly the same speed. It's kind of a cool thing to actually watch that happen out there in space. So remember, gravity is this force that pulls things together, right? Think bungee jumping. Like, oh, here's my bungee jumping video. They're like, no, I don't want to go, but you are. So that, gravity's affecting things. That's what's pulling things down. Weight, on the other hand, right? Weight is just the measurement of how much you're being pulled down, right? And so the big thing we want to get into today is the difference between weight and then mass in a second here, right? Weight is how much gravity is pulling on you, right? So that's why, your weight can change. Let's say if you have a bathroom scale and an elevator, right? Do this, right? When you go in an elevator, when you're going up briefly, your weight's going to increase. When you go down, your weight's actually going to decrease when you start going down, right? Your weight, realistically, if you had a sensitive enough scale, right? If you were down at the beach, right, and you weighed yourself, you would actually weigh more than, let's say, if you went to the top of a really, really high mountain. You'd actually weigh just a little tiny bit less because you're further away from Earth's center, right? So there's less gravity pulling on you. Now, mass, on the other hand, I always like to think of mass as, think of it as counting how many atoms are inside of an object, right? So like if you have a coin, let's say, and you counted how many atoms are inside of there, well, that doesn't change. It doesn't change if you're in space, doesn't change if you're on Earth, doesn't change if you're in an elevator, high up on a mountaintop, down at the bottom of the ocean. The number of atoms inside of the thing stays the same. And so that's why scientists often like to use mass, right? Because they're measuring how many atoms are inside of things. Whereas weight, right? Weight, let's say if you were measuring something really important like gold, right? I mean, you wouldn't want to buy gold one place and sell it in another place if they're weighing it, and you're trying to figure out like how much it's worth. You could lose a lot of money, or I guess gain a lot of money depending on how you did it. So what you want to do next is flip on over in your workbooks, right? Remember, these workbooks are going to get handed in just about a week or so, maybe a week or two. We'll get to handing in your workbooks, and all the pages get checked. So on page 43, they have a couple questions, and we can go through the answers together here, right? So for number one, true or false? On the moon, your mass would be less than it is on Earth, right? So here you go. If you go to a trip on the moon, would you lose weight or gain weight? You're going to definitely lose weight. So this is going to be false, right? This is going to be the answer for number one. Number two, this causes a sled. Where's my sled? Here we go. To go down the hill. Well, sure, that answer is gravity, right? Gravity. If you ever like sledding, skiing, snowboarding, then you like science. Number three, the strength of this, wait for it, depends on two things: how hard the surface is pushed together and the type of surfaces involved. And the answer is going to be friction, right? So friction, and two things are moving past each other, right? The two big things that matter are how smooth are the two surfaces, right? Surfaces, and then how hard do they push together, right? If you push really, really hard, that's harder to slide. Let's say here, weight is a measurement of what, right? Gravity, right? Falling and everything. We're halfway. Number five, the size of the force of gravity between two objects depends on, come on, you can guess it, the mass of them. Yes, the mass of them, right? And the distance between the two of them. Let's see here. Mass is a force that's measured in, can you get it? How about a hint? Grams. Number seven, we're almost to the end, right? The force of gravity on a person or an object on the surface of a planet is called simply, right, your weight, right? That's what we measure commonly and everything. And then last question, and we're out of here. The very last question for the page is, the law of universal gravitation states that any two objects in the universe with mass are what towards each other? You got it. Attracted to each other. All right, so make sure that you are filling in your workbook. Remember, in the physics folder on Schoology is basically the answer key to the workbook. So if you have any questions about any of the pages, you can always check that. Also, remember, you can check on Schoology right on the agenda, like which pages in the workbook have we covered so far, so that there's no question like, oh, did I have to do this page or that page? All right, make sure it's all caught up, and I'll see you in class.